time we talked about capacitors. And what I want to talk about now is the graphs you get with capacitors. And the graphs for capacitors are actually exponential.
So what is the topic?
It's still capacitors. We're still continuing where we left off with capacitors. Okay. Where's my pen gone? Whoa. Whoa. Whoa.
So what, can I just write the topic as a graph of capacitor?
Sure, go nuts. I'm trying to find my pen. I've lost my pen. Turn the music off, Joshua. Was he, wasn't it, Joshua? Ah. Sorry. I think I'll have to. I think you get your wish, Tal.
Yes, finally we're doing something in the normal way. No technology.
All right. Today's lesson on the board. Technical problems. Okay, so your capacitor, if we were to do a graph of it, you can actually see the graphs there on the bottom of page 32. See those two graphs there? Yeah. So on this one here, the first one, time and current. Okay. What's wrong? Just focus, please. Okay, so we have our capacitor, and we'll just put it with a resistor and then our battery or something like that. And we have it turned off here. Okay. And okay. So here I'll put my ammeter. So I close the switch and the current goes around like this, of course. So at the beginning, do you think this value on the ammeter is big or small?
In the beginning, 0.
In the beginning, 0. And then what happens?
The capacitor gets charged, and then the charge goes around the...
Yeah.
And then what happens?
With this here, when I close this, the current builds up here. The charge is inside here. So there's not much charge going into this. And then when this is full, then the charge is as normal. So the graph would look like this.
Which is what? Which?
And here, this is time. And here, this is current. So you see, during this part here, this is when the capacitor is charging up.
But the book says different.
No, that's discharging, which I'm going to do next. Yeah. So, the capacitor is charging up. So it's charged. Now what we need to imagine is I take this, for example, and maybe I put it over here. So this has a charge. I don't know. Another resistor here. And then again, I have my ammeter. Or this could be a light bulb, just some resistor. This time, the capacitor is discharging, it's losing its charge. And the graph would look like this. So here's time, and here's current, and the graph is decreasing, like that. whereas the number here is going to be the same as the number here, which they usually call I0. I0. This graph you've actually done in maths class. This graph here is exponential. So the graph is like of this form. I equals I0 e minus some constant called tau. I think they use tau in the book as well.
Tau is something C.
Or C is what you're thinking. They just use C or, yeah. Do they just use C or? Oh no, they use capital T. I think in your formula book for the physics exam they use tau. Okay, so let me just fix that. So I'll just write a note here. And they use big T, whereas in the formula book we use tau. Looks like a T. Its name is called the time constant. And in the formula, it is small t over big T, or tau. So what happens here is, because this is negative, it's decreasing. It's called the time constant. And there actually is a formula to work out the time constant. And it's a simple formula. The time constant is equal to the resistance here, or multiplied by the capacitance here. So the two formulas we have for the first class are these two. Can I remove these?
How do I define I0?
Yes. Well, that's what I'm going to do next. Is how could you find these constants? You mean from like an experiment or something?
Yeah, I mean, is it so? I0 is a constant
I0 is a constant
for all the capacitors, or for?
Oh no, for this capacitor here, for this experiment here, yeah. So the two things which you will have that are different in each question will be the I0 and the time constant. They're the constants which are different each time.
And they will give it to us, or we have to find it.
Yes. I mean, if they don't give you this, then they'll give you these. You know. And the I0 could be from a previous part, like use Ohm's law to calculate the current. Something like this. So like, I mean, we could do that as an example. So before I go on to doing that, I just want to talk a bit more about this. I equals I0 e minus t over time constant. This graph is fine, but in your exam, they usually want a straight line graph. So then the question is, how do we change this into a straight line graph? And we use what we've been doing in maths class. We use log. We put log on both sides. Now, I can use my first rule of logs. I get log I equals log I plus log e minus t over time constant. You okay, Dana? You understand? Are you sure? You don't look happy. Okay. Now, here, what happens with this power? You can bring it down. So you got log I equals log I0 minus t over tau log e. But who knows what log e here is?
1.
it's 1. So you are left with log I equals log I0 minus 1 over tau times t. Or if I write it the other way, log I equals minus 1 over tau t plus log I0. And the reason I'm writing it like this is to make you see the comparison with this equation from maths. Y equals mx plus c.
So why do you answer log E?
Log E, yeah. ln E equals log E, which is 1. Can I remove this here on the right? So what I'm saying now is if you make this graph where here you put time, but here you put log I instead of I, then what shape graph will you get? It'll be a straight line. And what's the slope of this line equal to?
Minus 1 over tau.
Minus 1 over tau. So in fact, you could get the time constant from the graph. Time constant will be minus 1 over the slope. Like that. Okay. So I have seen this question in the exam before, an exam question. They give you this table. Here is t, and then here is, for example, log I. So we'll just say 0, 10 milliseconds, 20 milliseconds, 30 milliseconds, 40 milliseconds, something like that. And then log I, well, I don't know, we'll just say here, I think, I don't know how, I'll just make it 2. 2, 1.9, 1.8, sorry, I didn't put the units in, 1.7, 1.6. Log I, so it's still going to be amps. So I'll just write in L.
Are we supposed to put the M on the first element, like units at the left and this?
Oh, I put them in my table, but I should really put them in here, yeah. Like you should really say MS here, but it doesn't matter.
Would there be a marks deducted if I put M2?
Oh no, because this table was given to you.
Oh.
Yeah, so I'm just writing down the numbers. And the question asks you, number 1, to plot or to draw. And then number 2, they wanted the slope. Okay. Number 3, they wanted the C, where it crosses here, which I haven't actually said yet. This here is C. This is the slope. And what does the C equal? That's log I 0.
Where is C?
This number here. Yeah. Well, not C capacitance, okay? So maybe not to confuse things, I'll say intercept. Intercept equals log I0 for here.
But the axis is log I.
Yeah. Yes. I just mean the C here in the line, the intercept. So they wanted the slope, then they wanted the intercept. Okay. Then, what else would they ask for? They would want I0. And then I think finally they wanted the time constant, yes. And then once you have the time constant, you know that tau equals RC. So if I give you like the C, you could get the or. So, No, it's usually C. They want the capacitance C. So they would also say in the question that the resistance is like 100 ohms in the circuit. So here's the capacitor, and then here is the resistor, and then they connect up here a ammeter. And this is 100 ohms. And I've seen this in the question. Okay, so I'd like people to do this now for me. Now it's only 1, 2, 3, 4, 5 points. Okay, so it shouldn't take you too long to draw. But try to draw it roughly accurate. Okay? At least use a ruler if you have a ruler. Do you have a ruler? No. Okay. At least try to do it nicely. Oh, and one last slide, just before you start, one thing I haven't said, which is important, with the time constant. This number here, this is important. This number here on the graph, when the charge is gone, okay, that is always considered 5 multiplied the time constant. So that's another useful thing about the time constant, is if you know the time constant, and I ask you how long until there is no charge left, it's always 5 multiplied the time constant. Okay, so once you have that, you can now answer this question. Time to no charge. How long until there's no charge? Yes.
The 5 is time when there's no charge.
Yeah, in other words, how long it takes for the capacitor to lose all its charge. It's discharge time.
And the C is the time constant.
The tau.
No, yeah.
The tau is the time constant. Sometimes people use a big T. In your formula book, I believe it's tau. 3 and 4. It's okay? I'm just trying to check here for you, Tanish. Yeah, there you go, Tanish. The time constant is that symbol there. Can you see the tau symbol equals RC? In this case, the big C is capacitance, yeah. Yeah.
And the C over there, the small one is constant.
Yeah, unfortunate. Oh, wait, and my question?
No, the formula I.
Oh, yeah. That C there is the, not capacitance, yeah, it's the C in the equation of a line. In fact, maybe I should go American here and use B because that's what they use in the States.
Is it okay that the time constant is negative?
It is not okay, it means I've negative back numbers.
The slope is 10.
Is my numbers here not, they're not big enough or small enough?
I don't think the slope is 10. So 10 equals minus 1 over
Oh.
tau.
How would the slope be, my graph is going down, for sure. So slope should be negative. Like I can see a graph there. That graph has negative slope. That's the graph you drew, yeah?
Oh, it's minus 10.
Yeah. That freaked me out.
What is the unit for time constant?
Well, resistance is ohms and capacitance is farads. So it'd be ohm farads.
The slope is 10. Minus 10.
Slope is minus 10, yeah? So if you've got slope is minus 10, then that means the time constant is 0.1. Also, I should remind you, my time is in milliseconds.
Yeah, so
That's
yeah.
why it's 10. That's why it's 10.
Because it's milliseconds, okay.
I'm changing it to second.
Yeah. That's good, yeah.
Yes, that's what I said.
Yeah, that's my point.
This constant has unit.
It does ohm farads. For which constant?
The constant equals to minus 1 over
The
No,
time.
that's constant.
I think the time constant has units of seconds. Yes, it does. It's units of seconds. Yeah.
The capacitance is pretty big.
Yes.
And this is 1 millifarad.
Nice. Oh wait, how much? Milli or
Milli.
milli? Oh, that's not too bad. I thought you said 1 million farad. Like nice. Millifarad. I can. It's pretty big, but I can live with that. Yeah. If you said something like a kilo farad. Okay. Let's have a look at this here. So I have my time, which is 0. What's the next 10 milliseconds? So that's 0.01, 0.02, 0.03, 0.04. And my current, 2, 1.9, 1.8, 1.7, 1.6. Okay, and now I'll draw my graph. Insert chart. Scatter. That one there. What's that? Yeah, go ahead. Okay, that's okay. Just get the notes from someone then. Yeah, that's fine. Okay. X-axis time, y-axis current, or it's really the log of the current. And that's in amps, and then that's in seconds. And my graph, we'll just call it. Okay. Sorry, it's kind of, can't quite see it, can you? It's a bit big. Let me shrink it down a bit. Okay, you should have something like this in your notebook, yeah? So let me just put in the trend line. Yeah, very good. So you can see here.
Can I ask one question?
Yes. Can I remove this? Yeah, go ahead.
The last question, time to no charge. If I equals to 0, so then
Excellent question. You can see this is part of the problem. This equation is, it's really an approximation.
no, I mean if I equals to 0, so ln I is also 0, right? Or it's 1.
If I equals 0, then ln I should equal 0. But you won't get the time constant from that.
No, I already get time. I need time to no charge.
And you won't get the time that way either. I
I have time constant. I have intercept.
No, I just want to make a remark here. Remember I told you this graph never crosses the x-axis. Remember I told you that? Yeah, it never crosses the x-axis. Which means this is never 0. But I just told you that it'll take 5 tau until it's 0. Now, what's really happening is it's so small here, you take it as nearly 0. But the problem with this equation is that it's smooth. What I mean is the equation looks like this. But what's really happening is this. Charge moves with electrons, doesn't it?
Yeah.
So the graph is really going like this. But you can't see that because the electron charge is so small. So this will hit 0, but my blue graph doesn't actually reach 0. So we say that 5 tau is when it's roughly reached 0. Yeah. Now, look, if you try using the equation, what you just said, what is it? Log I equals
Minus 1 over t.
minus 1 over tau
times
t plus log I 0. You want the time for when I is 0.
I have I 0. I have tau.
Ah, yeah, but if you put I 0, you get this log 0, which is minus infinity. It has no value.
Yeah. So how are we supposed to do that? That's the one equation.
The only way to do it is by use of this fact.
Why it's 5 tau?
The reason for 5 is because for this graph here, after 5, it's a convention. It's just considered that after 5 time constants, it's so small we can take it to 0. The choice of 5 is just a choice people have agreed. It's not it doesn't have any special reason. It is 5 because that is when it's so small we can take it to 0. I mean, it must be that after 5, the I here must be smaller than the charge of 1 electron or something like this. it can be taken to be 0. But there is no reason for it. It's just, you know what I mean by convention?
So how do we write our equation?
Oh, that, just by that. That the time to reach no charge, you can take it as a formula, is 5 multiplied the time constant. As a fact, as a formula.
Okay.
Here, why don't we put, if we put this in, let's see what happens, okay? So we get log I equals minus 1 over t, 5 tau plus log I 0. That and that cancel. You get log I equals, well actually, let me put it back into the one up there. I equals I0, e minus t over tau.
It would be easier to do it with log.
I think for me it's a little bit clearer.
We have the values for all the logs.
Oh no, but for me, what I'm about to say, it's clearer this way. 5 tau over tau. So you get I equals I0 e minus 5. Now if you type in e minus 5 on the calculator, what's that?
6.738 times 10 to the power minus 3.
10 to the minus 3.
Yeah, but it's 6.7.
Okay, I'm just getting it roughly right now. Now we usually use milliamps, don't we? So like for example, if this I0 was say, I don't know, 100 milliamps, as an example. 100 milliamps, how big is that? Minus 3, multiply 100, multiply 10 to the minus 3. That is 100, 10 to the minus 6 microamps. See, I'm saying it's not perfect, but what you're doing is you're saying it's so small that we take the charge to be 0. But the formula never actually makes it to 0. 100 microamps is really, really small. We often just deal with milliamps. And in fact, microamps will be less than what the ammeter could measure. Like this ammeter could only at best measure, I think, to 1 milliamp. So really, 100 microamps is 1/10 of a milliamp. So it's so small that we take it to be 0. Okay, but there is no good reason other than it will be really small. So that's why we take it as 5. And this is normal.
This would be always 5.
This is always universal, every physics book, 5.
So in the exam.
In the exam, take 5. Yeah.
Then will they give us 5 or will we have to?
No, this is something you need to know for the exam. Yeah, 5 tau. Yeah. Okay, I can remove this little piece here. Okay. Now back to my equation up there. I have y equals minus 10x plus 2. So I've got the slope, I've got the intercept. Now I want the I0. So which one do I use for I0? The 2, isn't it? You have log I0 equals 2. So who knows what I0 equals? What would it be here?
2 divided log.
No? It's e power 2. What's that? 7.389 amps. Okay. And then I also want the time constant. Well, before I get the time constant, I need to actually also get the slope, the time constant from the slope, sorry. So time constant equals minus 1 over the slope, which equals minus 1 over minus 10. So that equals 0.1 seconds. Now, next, I want the capacitance, so I can use this formula. Tau equals or C. So C equals tau over or, which equals 0.1 over 100, which equals 10 to the minus 4, or minus 3, which is what you said, milli. So you have 1 millifarad. No, sorry, what am I doing? It's F, isn't it? Farad. And lastly, the time until it's all discharged is just 5 times the times constant. So it's half a second. That's that one. That's that one. Time constant, that's part 5. The I, that's part 4. The slope, that's part 2. The intercept, that's part 3. And then the graph, that's part 1, which I drew up there.
So is that a new formula? I mean, tau equals to RC.
Oh no, I wrote that earlier. It's a formula to calculate the time constant. If you know those two little pieces of information.
The charge would be with this time 0.05
Oh yeah.
amperes.
The charge at this time is 0.05 amps. Yeah, I would have preferred it to be a bit smaller. I think the problem is my question, I made these numbers too big. They should really be 0.2 amps. In the exam, you should draw that graph on graph paper. They give you graph paper, okay? We'll talk more about that. Okay.
RC.
And I want to have a look at some basic electricity questions in the exam now, okay? So far we've done Ohm's law, really. We've done 3 things, really. Ohm's law. What's Ohm's law? V equals IR. We did the law for resistance. There was 2 formulas. We did the law for capacitance. There's 2 formulas. And now today we did the graph for the discharge of the capacitor, when the capacitor loses charge.
Energy storage.
And we also did energy stored in the capacitor, a half CV squared. So I want to, rather than going on to something new, I want to try and strengthen this knowledge by looking at exam questions on these topics. Okay, so the first one I have up here, you can see it's a section B question. Part A is all about capacitors. So the first one, a 2 microfarad capacitor is charged. So it's charged, and the voltage is 100 volts. It is then connected in parallel. So what's parallel? That's this one, isn't it? With uncharged 4 microfarad capacitor. Calculate the charge, determine the initial charge stored in the 2 microfarad capacitor. So there's only one formula here you need. What's the formula for charge? Q equals CV. Do you know the C? Yeah, and do you know the V? You do. So really quickly, you can tell me what the charge is. So work on that for 1 minute. Yeah, I just want you to do this part. So the formula you need to use is this one. Q equals CV. Oops. What is it?
200 microfarad.
Yes. Well, we'll have a look at the answer here. Has everyone done it now? Yeah. So if you look here, Q equals CV, which is 2 times 10 to the minus 6 times 100. So what's the 100 here? That is the voltage, isn't it?
Yes.
And then this is the capacitance. So this comes in at 20. Did they make a mistake? 2 to the minus 4 coulombs. 2 times 10, 20 millicoulombs, or as you said the other way, 200 microcoulombs.
It doesn't matter.
It doesn't matter. If you left it like this, that's fine.
If I, so,
It doesn't matter, yeah. So here we have C is, sorry, what was C? I don't have it here.
2 microfarads.
2 times 10 to the minus 6 times 100. So that is 2 times 10 to the minus 4 coulombs. It's only 1 mark, so it's not much. The next one is calculate the potential difference across the capacitor combination. So now you put the two capacitors together and they want the voltage. Okay, so this might take a little bit longer, so have a think about that. Okay, you still need to use Q equals CV, but now the capacitors need to combine together. So when they're parallel, do you remember how to combine them if they're parallel? What's the formula? C equals C1 plus C2. I'll give you a minute to try that, okay? So I want the voltage in the combined case. It's actually still the same formula. I don't say it out loud, but if you haven't finished, let me just see what you got. Yeah. Yep. Yes. What's wrong about it? Oh, you need the question back, sorry. So 2 people have the right answer so far. Anyone else? Correct. You have the answer? Okay. What's this? Do you use this formula? I'm sorry, use the other one.
Why?
For capacitors, when they're parallel, it's C1 plus C2. You confuse parallel and resistors, yeah. So you have the right idea with the rock formula.
You have 2 capacitors.
Let's see. Yes, it is. What did you get? Which is what? 33 or 333?
Because I didn't change it.
Not because, what did you get?
333.
No.
Okay, everyone has the right. Oh, but some people have micro and some people. Okay, yeah. So it depends if you use micro or milli or whatever. But everyone's answer should start with a 3. Yeah. Now, what formula did you need? You needed Q equals CV. So you rewrite it and you get V equals Q over C. But we need to use the total C. So you add the two together. And the Q is not changed because it's still the same charge. You just connect it to another capacitor. Okay, so try not to die. Okay, so just really quickly. Here, so that's part 1. So part 2. V equals Q over C, but here it's Q over C1 plus C2, which is 2 times 10 to the minus 4 over, what was C1 and C2, what are they? 6 milli for both or total? Total 6 micro. Yeah, so this ends up being 0.33 times 10 to the 2. Is that right? Yeah, so it's about 33 point, roughly 33.3 volts. Now, this is important. You might say here, why is it Q and not like Q1 plus Q2 as well? Yeah, well, I want to show you that in the question. Look up. You see here, it says the 2 is, look up everyone, the 2 is charged. And then the 4 is uncharged. So there's only charge in the first one. So the charge in the second one is 0. Okay. Can you do part 3 for me, which is the energy, the final energy stored on the capacitor combination? So in other words, at the end, what is the energy? Now, do you know the total capacitance? Yeah. And do you know the voltage? Yeah. And what's the formula for energy? FCV squared. Do you know how to use your calculator? So give me the answer.
3.3 times 10 power.
Yeah. 3.3 times 10 to the minus 3 joules. Using a half, no, they use that, it's the same answer, a half QV, or you could use a half CV squared. Whichever you prefer. I think this one actually is a bit quicker. The reason it's quicker is because you have these two answers already to just multiply, isn't it? But anyways, did everybody here use a half CV squared? Yeah, and you got the same answer? Yeah. Now, I'll just quickly write that down. 3 energy equals a half CV squared. Okay. The C is 6 micro and the V is 33.3 squared. So this is how much?
3.3 times
3.3 times
10
yeah.
power minus 3.
So milli.
Power 3 negative 3.
So millijoules.
That's
Okay. How many marks have you gotten so far with those 3 questions? 6. How many formulas have you used?
2.
2. What are the 2 formulas you used?
Energy and
Q equals CV. Oh, actually, we really used 3 because we used Q equals CV. C equals C1 plus C2. And then energy equals a half CV squared.
Omega is
10 to the 6. Yeah. Now, the next one is now what we did today. If the capacitor is then allowed to discharge, and that is the resistance, 5 mega ohms. How big is mega? 10 to the 6. Calculate the time taken until the voltage is 10. And what's the voltage at the start? We have that from the previous. What's the voltage? 33.3. And then what happens? It discharges. Do you want, well, I can give you some of the steps.
No, just
Oh, I'll check your answer in a moment, yeah. Now, can you, actually, just before you started, let me just give you some preparation for it. We have this formula, I equals I0 E minus T over time constant. We just did that one today. Okay. Now, come on, please look up. This formula here is also true for voltage. You also have the voltage equals the voltage at the beginning multiply the time constant. Okay. And you might say, why is that? Well, if you look up here, oh, stupid colours. I only have blue left. If you multiply, look up guys, if you multiply both of these sides by or, what does Ohm's law say? V equals I or. So this is the V, and then this, because it's I0, then this is the V0, the voltage at the beginning. So you can see that it's the same formula. Okay, now that you have this formula, you should be able to do it. So I'll give you a minute to try it, then I'll do it. But you want to quick check the answer, yeah?
You show the question that.
Yes, in a second.
Yeah.
Okay.
When we will do magnetic and electric fields?
Next semester. So we have these section B questions. You have to do 3 of them in the final exam. They're each worth 20 marks, so it's 20, 20, 20. You already have out of the electricity question 9 from 20 done. It's okay. Okay.
Will we finish this book?
So can you do
So we'll finish this book we'll finish this book and the next book this semester. There's this book and another book for this semester.
What's the other book about?
Waves. Okay. I want to see if someone has, if people have answers, I want to see what you're getting. You got the answer? And you know that yours is right. Good. Yeah. Okay, so in 1 minute I'll do it on the board here. Can I? Another minute and then I'll do the answer. Okay. Can I scroll down? Can I do it now? So here, what's the voltage at the beginning? 33.3. And what's the voltage you want? 10. And we want the time. Do we know the time constant? What is it? Yeah, well, I think you have to work it out, isn't it? That the time constant is RC, which is, how big is the R? 5 mega, and the C is 6 micro. Oh, so it works nicely as exactly 30. Oops. Now, what I'll do is, I'll bring this down here. So can someone tell me what I have on the left now, please? 0.33, yeah? Well, if I divide the top 0.3.
Yeah.
Exactly. Okay. Now, does anybody know what I should do here? Yeah, I should put a log on both sides, because like what we saw in maths class, this power can come down. But what's log of E? 1. So you have T equals minus 30 log 0.3, which is 36.1 seconds. I know it's a little bit difficult, but I mean, it's not the most difficult thing in the world. Especially the first part where you had Q equals CV. Okay. Did you write this down? Yes? Okay. So we were able to do part A, 9 marks. 9 marks. Let me just have a quick look at section A to see if there was anything there as well. So here we have no. Remember this one?
Yes.
No. Here we go. Okay. So this we'll do. Well, this is a thing I'm going to do next in the book, so we might as well talk about that before I look at this question. Okay. Okay. Now, here. Uh-oh. Okay. Here's my simple circuit. This is a light bulb. So this is doing work. And then this is the battery here. And the current is going this way here. The reason this can do work is because of the battery. Yes? And what from the first part of the course is the formula for work? In the first part. Force multiplied distance. Okay? But in this example here, there is no force. It's just a current, a charge that's moving. Yeah? There is no force here. But from the first part of the course, we still know that work is force by distance. And what you need to picture is that there's some special type of force inside the battery that is giving the charge its energy, that's moving the charge. Okay? So there's like a force inside the battery. Is it to do with the mass of the electrons? No, I don't think so, actually. There is actually no formula for this force. This is more just about an idea I'm trying to get in your head. Newton says that when you have a force, you have work. So the opposite is true. When there's work, there's a force. But in this diagram, there is no force. And that's because the force you cannot see. The force is inside the battery. The force is inside the battery, or the cell, we call it. We don't see this force. We can't calculate this force, but we know that the force is there because it's doing the work. And this force inside the battery has a special name, which is called EMF, which I think is the next thing in your book here. Actually, yeah, it's a little bit ahead. It's actually, you need to look on page 42 for the definition if you want to have a look. Electron. Okay, English time.
What?
English time. So, force.
I don't want to speak with me in Russian.
Sorry. Force, we know what force means. What does this suffix mean? What does motive mean?
Movement.
Movement and motion. So this one here, means move. And what do you think electro is?
Electricity.
Like electricity or electron. So EMF is the force that moves the electrons. One of these situations where English makes sense. Yeah. So electromotive force is the force that moves the electrons. Now, that definition is, not a formal definition. It's just a definition to get you to understand it. Okay. In the exam,
Can you also describe the work done to move current through envelopes?
yeah, this is now getting into the formal definition. Yeah. If we look at the exam, EMF of the power supply is the energy converted into electrical energy when a unit charge passes through it. So this is the very, very formal definition of it. You should write this down, actually. I'll talk about it now. I'll explain what this means now once you write it down. Okay. Do you have that written down? Yeah. Do you remember my definition of 1 volt?
No.
So I said, no, for real. So I said, if there's 1 volt from here to here, that means when 1 coulomb of charge moves, it does 1 joule of energy. That's what it means to have 1 volt from here to here. So 1 volt from A to B means 1 joule of energy when you move 1 coulomb of charge. Okay? Now, if you go back to my picture here, what is the work that's being done here? What's the work being done?
Yeah,
The light bulb, isn't it? That's the work that's being done. And where's this work coming from? The battery. The work that the light bulb does equals the work that the battery does. So how much work comes out of the light bulb is how much work the battery is doing. So the other way to think about EMF is how much work you can do, which is what that definition is. That definition says EMF is how much work you can do when 1 coulomb comes out of the battery. Yes? So if 1 coulomb comes out and you can do 100 joules of work, then we say that the EMF is 100 volts. So the unit for EMF is also volts. Okay? In other words, EMF is a lot like the voltage of the battery. It's nearly the same thing, in fact. So when you have a battery of 1.5 volts, the EMF is nearly 1.5 volts. It's like 1.4. Does anyone know why it's a little different? And the reason is the work that this battery does not equal the work this does because some energy is lost. What form is the energy lost in? Heat, isn't it? So when you have your battery and it feels warm, that's work you don't want. So it means that your 1.5 volt battery maybe has an EMF of 1.4 volts, meaning it can do 1.4 volts of work. Okay?
Where did the rest go?
And it's lost its heat. Yeah. So EMF is similar to battery voltage, except it's smaller. It's a little smaller. You need to learn that definition for the exam. But I hope that picture is clear in your head that EMF is battery voltage. It's work that can be done. Okay, so we'll go back to the exam question now. Okay, I think we'll do these two together and then I'll let you try this one. So here we have two batteries. Look, two batteries, volt and current. Now watch carefully, I'm going to show you where the current goes. The current goes around like this. Okay, the current goes around like this. Yes? Because remember the voltmeter, this is like A and this is like B. It's telling you the voltage that's around the resistor. So if my current goes around this way, does any current go through here?
No.
No. So that actually tells you what the resistance here in the voltmeter. This voltmeter has resistance inside of it. Whoops. And you see, it must be very high. Why must the resistance in the voltmeter be very high?
So
Because
that
so no current goes through it because the voltmeter only wants to look at the voltage. It doesn't want any current. So it has a high resistance, so no current can pass through it. In other words, it's a bad conductor.
Do all voltmeters have some?
Yes, all voltmeters have a high resistance. Now, does the current go through A, the ammeter? It does. So because the current goes through the ammeter, must it be a good or a bad conductor?
Good.
Good conductor, so therefore the resistance is low. So it has low resistance. So part 1, the voltmeter must be made with high resistance. Part 2, the ammeter must be made with low resistance. And this, Tanish, is true for every voltmeter and ammeter. Okay, so can you just make note for those two? B for part B1, B2 next now. So the first one is a high resistance voltmeter and a low resistance ammeter. Okay, do you write that down? Yeah. So let's have a look at the next part. So for this part, it uses the same diagram. In the circuit above, when the switch is open, the voltmeter is 8.3. And when the switch X is closed, the voltmeter is now 7.58. So why did this change? Why did this change? Why did it decrease? No? Well, the reason for it to decrease...
Because there's work done in the battery.
Not quite in the battery, but you nearly have it. When the switch is open, does the current go through the resistor? No. But when the switch is closed, does the current go through the resistor? It does. So this means you have a different resistance, so you have a different voltage. Because what's the formula? V equals IR. So the voltage changes because the resistance changes. Do you have more or less resistance now?
More.
You have more. Okay.
So EMF is IR plus R.
Capital I, R.
Yes.
Capital I, small.
Yes, we're getting, that's the idea of the formula. But that's to do, you know what the small R is?
Yeah, the
The internal resistance, yeah. And then the current through the ammeter is 3 amps. So the current is 3. So what is the EMF, the power supply? What is the value of the resistance? Or determine the internal resistance, the power supply, and determine the power consumption in R. Now this question is very tricky. So actually, maybe I need to... No, I'll let you try it first. You
So
might...
do you think give us the formulas for it?
Yeah, but you could work it out from using Ohm's law, which I'm wondering if you can. No, okay, no, that's too mean of me. No, we won't do it just yet. So we need to talk a little bit about EMF. Yeah, okay. So before we do this one, a bit of notes. So when we have our battery, here it is here, we need to picture our battery like this. Like that maybe. So this is the picture of our battery. This here is the voltage. It is the true voltage. This is the EMF. But we never ever get this because some of the voltage is lost here. There's like a resistance inside the battery.
Oh, is that a battery?
That's like a battery, a simple picture of a battery. So the battery has a voltage, which we call E, and it has an internal resistance, which we don't know, and this is the cause of the heat in the battery. Okay? Yes? Okay, so we can connect it up here. And let's connect it up to a big resistance here, or. And then we can connect it up to an ammeter here as well, A. Okay. So let's imagine we measure the voltage here. And let's call that big V. Okay. Can we measure the voltage here of this small R? What do you think? Can we measure it? Can we measure this small R? Can we measure the voltage here? No, we can't. Why not?
So what's the question?
Alright, are we listening now?
Yeah.
The small resistance inside the battery, can we measure the voltage around that? No. Why not? Anyone? No? Okay. Because
there is current.
No. Because it's inside the battery, right? It's inside the battery. And besides, this isn't even a real picture. Batteries aren't made like this. It's not like when you have your battery and you open it, there's a good battery and a small resistor inside it. Yeah? It's only a representation. Alright? So firstly, there is no small resistor inside the battery. And secondly, even if there was, we can't open the battery. So we can't measure that R. But we can know it from using Ohm's law. What does Ohm's law say? Yeah, that the voltage here is actually IR. And if I didn't have this voltmeter here, if I didn't have it, what would the voltage here be? It'd be I big R. And then this one here is I small r. So they're the two voltages, yeah? Now, what is the total voltage of the battery? Not like this example here, forget about the question. What's the total voltage here of the battery?
IR plus IR.
Yes, you're right. And another letter?
I.
This here.
Oh, E.
Yeah. This voltage is from the battery. That should match how much is in the circuit. Okay? So this is like the start. and then it goes around, and it has some voltage here, then it goes around, and then it has some voltage here, but this must equal these two. It's a bit like with our potential divider. Remember, we had like 100 volts, and we split it into, what was it, like 25 and 75. Do you remember that potential divider?
Oh,
Yeah, so the total must be E. So we have a formula, I, R plus R equals E. So I equals E over R plus R. Now, if I, right, do you need to write this down? Sorry. So I'll just write that down. Can I go on? I want to show you something in the formula book. Where is it? I'm looking for the formula, the EMF formula. To it is usually, isn't it? Well, it's not. Maybe it's in a different section. No. Yes. Yeah. This formula here, that's pretty much the same formula I have here. Do you remember? Originally I had the V here, yes? So another way to write this formula is E must equal IR plus V. And you can see in the formula book they have it just as what big V is. Big V equals E minus IR. So there's two formulas here, this one, and then this one here, and what's important is this one is not in the book.
So, but if I just remember that one, the one that...
Yeah, but it's not so difficult to prove because it just comes from Ohm's law. Yeah, so this one here is from Ohm's law. So you have two formulas here, and these formulas use V, I, small r, big R, and then big E here. Yep.
In the first one, V equals E minus IR.
Yeah.
Which one should be bigger, the E or
The E.
the V?
The E, which is bigger, the E or the V?
Which should be bigger?
The E should be bigger than the V. The E is always the biggest voltage in the circuit, yeah. Okay.
So when the switch is open in the circuit and I measure the voltmeter of the battery,
Yeah.
is that the error?
Not quite, because there's still a small resistor in the battery.
No, there's no resistor. It would have much more resistor if I close the circuit.
No, there's still resistance inside the battery. You can't get rid of that. You can't get rid of that. Now, can I go back to the question here? Yes, we do. We absolutely do. Okay. In the circuit above, when the switch X is open, the voltmeter reads 8.3. I'm going to draw this circuit when the voltmeter is open. Maybe you can help me remember. What was it? You had two batteries here, wasn't it? Yeah. And then the voltmeter was here. Is that right?
Yes.
and the switch was here, tal, and then the resistor was here, and it goes around like that. Okay.
The ammeter.
And where's the ammeter? Is it up the top or the bottom? Bottom, okay. Here is A. And the circuit goes around like this. But this switch is open. Do I have the battery the right way around? Is it this way around? Yeah? Okay. Then when the switch is closed, so I'm sorry, I've lost my colours here. I'll do this in blue. When the switch is closed, it goes this way. It goes down.
And it also goes
Yeah. But it doesn't go through the middle now when it's open. When it's closed.
Why doesn't it go? Doesn't just. Why not?
Because it doesn't, the voltmeter has a high resistance. It just measures voltage. No current really passes through it. I mean, there's a tiny, tiny amount, but you ignore it. Okay. Now, if you look at when the circuit is closed, can you see that it's actually the same as this diagram? You have battery, you have resistor, and then you have voltmeter. It's the same, isn't it? And then you have your ammeter here, isn't it? That is the exact same situation as what I just drew here. The same situation. So those formulas I have, you can use those formulas when the switch is closed. You can use them when the switch is closed. Now, with that information, and with these now two new formulas you can use with the switch closed, maybe you can try the question now for me. So here's the question again. What is the E, big E? So you have two formulas with big E in it. Now what information do I give you? This is the big V, this is the I. So try it for me, see how you get on. What's the resistance? Are you asking me the value or just the resistance? Oh, okay. Alright, alright.
Would you get rid of the highlights?
I'm sorry, okay. Do you by the way, do you have these two formulas as well written down? Yeah.
I got the answer, but I'm not sure if it's
Well, I'll just pop it up there here for you. Did you get this? 8.3. Yes. Yeah, it's a bit tricky.
Give it a try as a whole.
rush about it.
Yes.
Just work on a couple more minutes. I might give you some hints before you
We
go.
don't have a couple of minutes. Yes, we do. We didn't have a break before this test.
5 minutes max. Max. It'll be less than 5 minutes, okay? Yes. Good, okay. I can put the answers up actually. It looks fine.
Can you show a passive for the terminal resistance again, please?
No, actually, I won't.
Good.
I think what would be the best thing. This one is a bit tricky, and I think the best thing would be to leave it as a homework. Okay. Now, just so you know, this question is from a 2013 paper. So if you get really, really stuck, you can look at the answers on Moodle. Okay? I will do it at the start of the next class. But the formulas you need V equals IR, and then you need the 2 formulas from today. And there should be enough.
Yeah, it is now.
It is enough, yeah. So you need those 3 formulas. What's difficult is how to use the formulas. You asked me something earlier, Tanish, which I'm no longer sure about anymore, about measuring the voltage inside the battery.
Oh yeah, when the switch is open,
When the switch is open,
measure the voltmeter of the battery. It doesn't show 0, it shows some value.
yes.
Yeah, and then is that the EMF? I mean, because that's the charge flowing.
When the circuit is open,
Is-
the EMF is
yeah.
the voltage from the battery.
Yeah.
It is if there is no resistance in the circuit, no other resistors.
Yeah, apart from
Yeah.
the internal.
If you just have a voltmeter on the battery,
So to find the
Yes,
internal
yes.
resistance, we take the EMF
Yeah.
and divide it by the
so you
current.
have the E is 8.3. Yeah. And then you know those 2 formulas, then you know what the E is in each of them. So what'll probably happen is you probably get 2 equations with 2 unknowns.
No,
No, it's not even that difficult, no?
no. It's just straightforward answer.
No,
One
no.
divided by another. And
That's it.
one
There's no
divided
need
by-
to combine any of the equations. All right. So I guess it's not so difficult then. I'll leave it for you to do as a homework for tomorrow. Okay? And I might have your physics results then. Oh yeah. If anybody wants to know their maths result too, I'll be here for a minute. I can get on the laptop.